Continuing on with the exam review stuff, here is another problem where we have, let's write down our knowns. X dot naught is equal to 0. X naught dot is equal to 10. I'll stick with the millimeters in here, but I'll turn it into something else, right? So 0.01 meters per second is the initial velocity. Note that the amplitude, note there are multiple correct solutions. Okay, so this is sort of a design problem. What we're trying to do is find M, C, and K so that we have an amplitude, which they're calling A, by the way. That's going to be, well, it says less than 1 millimeter, but let's set it equal to 1 millimeter. And then anything that we do less than here will be less than that, right? I guess that's the idea. Okay, so we have to pick some. In the second problem, it says repeat the problem for this range. I kind of decided that I was going to use 10 kilograms when it came to the time to pick a mass. But let's proceed right here. So the initial position is 0. So that goes away and that goes away. So A is really going to be a square, well, it's the square root. I wrote it out here, so I want to go 0 squared plus velocity, which is 0.01 plus, well, this is 0 right here, so we just go, well, 0. We don't have to write the other stuff in there. And that whole thing squared divided by the damping squared. So setting that thing equal to 0.001, I can solve for what the damping is required for that amplitude. It ends. Well, let me like actually easier enough to reduce this stuff. Say A is equal to. Let me fix what I did right here. Okay. This was supposed to be X dot naught. Okay, so let's keep it generic. And I said that well, we'll have X squared is equal to X dot naught squared over omega D squared, right? So you can see that's true, right? Get rid of that. Get rid of that. All right, so we get X dot naught squared, right? So, and we had this. I guess maybe I'll take it this right here. I'm sorry. I should have just written what was on the page. I started trying to think and try to do things kind of differently, but I just want to fix this. So that means that A is equal to X dot naught over omega D. I do that right? Yes. So therefore, omega D is equal to X dot naught over A, which now we didn't even need to make turn these into meters, because they're just kind of cancel each other out, and you're going to have 10 over 1, which we know to be 10 radians per second. Okay, so here is the if that's the required damped natural frequency, what you could do, let's change colors so we can keep track of this. What we could do here is find what the from here we can find that oh, let me see, 1 second. Oh, I got you. Okay, so this is a design problem. So we go, ooh, let's find, we're kind of stuck at this point because we only know omega D. But it's there are multiple solutions. So let's like assume, which is the same thing as saying we choose squiggle equals 0.2. And how do we know how to do that? Well, after some experience, we can see that's a pretty common value for this damping ratio. It's not obscene. Like 0.8 would be too much. 0.001 would be too little. So if this is a damped thing, underdamped system, like as it says, we want to pick a very typical damping coefficient, and so that's the one we choose. And so we can now get the natural frequency that would result from that choice. This is a design problem, and sometimes design problems require you to make assumptions. I recognize if you are just starting out in design, you would find that to be very arbitrary, but design has to require some experience in what is a typical value. If you run across it enough, you will see this is to be true. We get 10.21 radians per second. Okay, so here is a design choice. Another design choice is how much mass, right? So we need we need to find some of the other things. So we need to choose the mass. Choose M is equal to 10 kilograms. And you say, why? Well, they gave us that range right there. It's on the lower end of the range. I might as well use the lower value. It's not, it seems kind of weird just to pick a value, but if there are multiple correct solutions, try it. If things get messed up, then try something else. So we know that using that the natural frequency is the square root of k over m. That allows us to find, because we already know this guy right here, we're able to find k is equal to m omega n squared. And so we take our 10 that we just chose and our 10.21 squared, and we're left with a k of 1,042 newtons per meter. So we're on our way, right? Because we were trying to find m, c, and k. So we have a m and a k. All we need now is a c. So we get our critical damping is going to be 2m omega n. Well, good enough. We have all of that information. Oops. Should be 10. And 10.21. So here's our critical damping is 204.2 newton seconds per meter. But we have already, what are we missing? Let's go maroon. No, we already used maroon. Purple. I didn't use purple on this page. So therefore, the critical damping, not critical damping, the damping factor is C over CC. So we get C is going to be equal to squiggle times CC. We got that already. 0.2, well, we got it, but we actually assumed it. And that's going to be 204.2. So we're left with 40.84 newton seconds per meter. So if we were to go to the answer to the thing, mass 10 kilograms, C 40.8 newton seconds per meter, K is equal to 1,000. We'll keep the 2 in there. So we've done a design in this problem. That's pretty cool. We've made design decisions. What are the design decisions that we made? We picked this and we picked that. Those are the only two, but here's a combination of values that will achieve the thing that we wanted to do. First, it was in the range of kilograms. It was just on the low end of the range of the mass. And also we can expect an amplitude that's less than 1 millimeter. Something to mention is this amplitude right there could actually be found from equations that we've used previously. So let's take a look at a damped system and look at that equation right here. Okay, so if we were to take this equation, I'm going to go highlighter. Let me go yellow highlighter. Yes, yellow highlighter. Let's take a look at that and recognize that the amplitude of it, orange, is going to be this, the square root of this squared plus that squared, right? So if we could call it big X, square root of X dot naught plus, okay, so these look a little bit different, but they're the same, over omega d squared plus X naught squared, right? So consider that, compare it to, all right, so let me look at that for a second, right? Consider this equation that we've used from up here and there. That's going to be the magnitude of this thing. And that is the same equation as this right here. Actually, that is a squiggle, because they go squiggle times, their squiggle looks different than my squiggle. But it is still squiggle, or xi. There you go. I have to go to a meeting, but I will make some more videos very soon.